Very much. It's a really great pleasure for me to be here, at least virtually, and to share my personal experience and also the experience of my team in distributed fiber optic monitoring with a special focus on geotechnical monitoring. As Jose already said, I'm from my profession, I'm a geodesist, so I studied geodesy at Graz University of Technology and also at Nottingham Trent University in the UK. Regarding measurement technologies, I do have a background in classical geodetic sensors, meaning total station, laser scanners, GNSS sensors, and also from my role as being a product manager at Leica Geosystems at the headquarters in Switzerland. Since more than 10 years, I'm full professor at Graz University of Technology, and there I'm head of the Institute of Engineering Geodesy and Measurement Systems. And because we do see that fiber optic sensing is really now ready to go on the market, we also founded a spin-off company last year. So this is ACI monitoring, and now we do the more, let's say, proven technologies from an industrial company side, and what is still research, this obviously stays at the university. As already said, I'm Vice President of the International Society for Structural Health Monitoring of Intelligent Infrastructure, so ISHMI, and I'm also President of the Austrian Geodetic Commission. As fiber optics may not be a known technology for some of the people in the audience, I'm going to explain fiber optic sensing briefly. So we're going to take a look in this webinar on some basics of fiber optic sensing, particular of distributed fiber optic sensing, but the main part will be geotechnical applications. So I've selected a few examples where we're going to take a look at the challenges, but also on the potential of fiber optic sensing. And what I also want to highlight today is testing and calibration is also a very important aspect in order to perform a successful fiber optic sensing monitoring project. So this is the program for today. So we have about 40 minutes time. And if you have questions, just type them into the chat or just ask them at the end of this talk. When we talk about fiber optic sensing, there are some common principles. And historically, fiber optic sensing started with sending light into a fiber and having one specific section of the fiber, which is having a strong back reflection. So historically speaking, sensing started with single point sensor. So in this case, these were very often interferometric sensors having mirrors inscribed into their fiber, and these gave a strong back reflection. And by, for instance, interferometric principle, it was possible to utilize light along the fiber as a sensing device. Very accurate, also dynamic measurements. However, the drawback here is you still need one cable for one sensor. It became more important and more interesting when we talk about distributed or quasi-distributed fiber optic sensing. So quasi-distributed fiber optic sensing means we have several measurement locations along the fiber. One example would be fiber break gratings. So fiber break gratings are wavelength-dependent mirrors, and here you can have tens of sensors along the same line, and this is already a big advantage compared to, let's say, classical resistive strain gauges. So with one cable, you can depict lots of measurement positions along your fiber. However, you still have to know where your region of interest is. So it works well, for instance, for joints. You know exactly where the joint is that you want to monitor. But if you have a large structure where you don't have any idea beforehand where the problems may occur, this is not the right technology. Here, distributed fiber optic sensing comes to play. Here the idea is we have a complete sensing fiber without any gaps. So we know at every location of the fiber what's happening. So we don't have any blind spots, and we can not just detect events, but we can also localize. So we can tell where something happened along our fiber. There are different ways to do that. There are single-ended configurations, there are loop configurations, but important is here it's about range and spatial resolution. So typical values are, if we go for long ranges, let's say several tens of kilometers, we usually have a spatial resolution which is the range of half a meter or a meter, so rather broad. spatial resolution, but very long ranges, well suited for long linear infrastructure like pipelines or railway tracks. Or we could go for shorter range, let's say a few tens of meters or maybe 1 or 2 kilometers. Here we can achieve a spatial resolution of about 1 centimeter. Either way, we are able to realize thousands of measurement positions with just one single measurement. So we send out one light pulse into the fiber and obtain a lot of information along that fiber. So this is the basic of distributed fiber optic sensing. And when we go further into that, we can also see different technologies in distributed fiber optic sensing. So let us first take a look at the difference between data communication and distributed fiber optic sensing. In data communication, the main goal is to transmit information along the fiber. So light is injected, transmitted, and the light at the end of the fiber is being analyzed. In distributed fiber optic sensing, we actually do not really care how much is ending up at the end of the fiber. We are working with back reflected light. And depending on the application, we talk about distributed strain sensing, so DSS, distributed temperature sensing, DTS, or distributed acoustic sensing. So one can think of that like thousands of resistive strain gauges, thousands of microphones, or thousands of temperature sensors along the same fiber. So how does this now work? If you take a look at a typical setup, we send it a light pulse into the fiber. And this light is actually being reflected at every location along the fiber due to natural inhomogeneities of the fiber. And this backscatter signal is sensitive to either strain or temperature or to strain and temperature. So let us take a look at this example. We send in a light pulse. We have a certain carrier wavelength and we send out a light pulse. Most of the light is being reflected at the same wavelength. So the back reflected signal has the same wavelength as the incoming signal. However, there are also other components being reflected. These are the so-called anti-Stokes and Stokes component. So some of you may have seen that graphic in different ways already. So one way would be if you take a look at the Raman backscattering. So this is further off the central wavelength. And here we have a Stokes and the anti-Stokes component. Interesting here is that mainly the anti-Stokes component is sensitive to temperature. So it's almost insensitive to strain and a strong temperature sensitivity in the anti-Stokes component. So what you can see here, if we would monitor the intensity or the ratio of intensities of the anti-Stokes component, then we can get information about the temperature along the fiber. If you're going to take a look at a different effect, which would be Brillouin backscattering, here we do see a wavelength shift. So we see a frequency shift in case of temperature and strain changes. And this enables us to get now information about deformation along the fiber. If we put some numbers to that principle, so when we take a look at Rayleigh backscattering, so Rayleigh backscattering is usually used in high resolution distributed strain sensing and in distributed acoustic sensing. When we talk about high resolution strain sensing, this means we have a measurement precision in the range of tens of kelvins and about 1 microstrain, and a spatial resolution in high resolution strain sensing of about 10 millimeters or better, but only very short range. Or when we talk about distributed acoustic sensing, here the spatial resolution is usually several meters, but we can go over very long distances, 100 kilometers, and with some special hardware, even longer than that. When we talk about Raman backscattering, so this is the classical way for distributed temperature sensing. Here we have an uncertainty in the range of hundreds of Kelvin and a spatial resolution of a few centimeters up to a few meters, and also very long ranges. Regarding strain sensing, for long distances, the technology to use is Brillouin-based measurements. Here, as I said, we are sensitive to strain and temperature, but with the right setup, we can compensate the temperature dependency, and we end up with a resolution in the range of 10 to 20 microstrain, but for very long distances, also about 30, 40, 50 kilometers, or even hundreds of kilometers. So these are a few things to note. So when we talk about distributed strain sensing, we work with natural back reflection. Here we have three different components. Could be the railway backscattering, which has the same wavelength as the incoming wave, mainly used for high resolution strain sensing and for DAS. We have Raman backscattering, where we have a temperature dependency, which matches an intensity change in the anti-stows component. And we do have Brignon backscattering, which causes frequency shifts when the strain and or temperature changes. So this is just a little bit of background. We're coming to that at the end of the presentation when we talk a little bit about calibration. But the main focus is now, how can this technology be deployed in geotechnical monitoring? So we're going to take a look at different geotechnical applications, and actually whatever you can think of has already been done with fiber optics. So fiber optic sensing or distributed fiber optic sensing has been employed already for tunneling application. It has been used for landslide applications. It has been used for concrete structures like bridges, piles. It has been used for joints, anchors, and pipelines, railway tracks, and furthermore. So actually what you can see on this slide are also all different types of projects that we have done so far. So actually we also have already used distributed fiber optic sensing for different types of structures. Could it be natural structures like landslides or rockfalls, or man-made structures, retaining walls, bridges, tunnels, pipelines, and so forth. And out of this selection, I have now chosen three different areas where I would like to show you what can be done, but also show you some principal challenges which are occurring when you deal with distributed fiber optic sensing. So the first example that I want to show today is an application which is about a reinforced earth structure. So reinforced earth structures are basically earth dams made up with earth, but also with some geotextiles or geogrids in between. And this specific structure, which you can already see here in that image, occurs at the tunnel construction site in Austria. As some of you may know, we are building currently three very large tunnels in Austria, one being the Semmering base tunnel, the other one being the Korm tunnel, and the third one being the Brenner base tunnel. Here we're talking about the Semmering base tunnel, which is a tunnel with two tubes, each 27 kilometers long. And what you can see on this slide, we have here three intermediate construction sites. We have construction activity at the portals, but also at three intermediate sites. Due to legal regulations, that material from those sites has to stay in the local region. So for all the material from these three sites with two tubes in both directions being built, it's actually 12 tunnel advances at the same time, there's only one single disposal site. And if this disposal site doesn't work, construction has to stop, because it's impossible to remove the material from the construction site. Then the central area is a disposal site. And how does such a disposal site look like in an alpine area? It's pretty simple. You have a valley and you basically fill up that valley. This is the valley as it was before construction activity started. What happened then afterwards? The trees have been removed, and now it's more or less prepared for the landfill. However, like you always have in those alpine valleys, there's a stream at the bottom of the valley. From a technical point of view, the easiest way would have been to put that stream into a massive tube. But however, this was not allowed due to environmental reasons. So therefore, the final solution has been taking this river stream, shifting up 50 meters into a new riverbed, which is supported by a reinforced earth structure, and then filling up the terrain. So in the end, this new riverbed will be finally again at the bottom of the newly constructed valley. And here, the big question was now, what happens during the construction phase? So after the whole well is being filled up, everything is fine, because then the retaining wall cannot fall over anyhow anymore. However, during the construction, it was planned to have a very high, very steep reinforced slope in order to maximize the volume that is available for the disposal site. So the disposal site has to be in operation at all times, and therefore monitoring was needed. And the monitoring system consisted of two parts. So one was to determine absolute deformations of the dam, meaning tilting or settlements of the dam, but also to get some information about the internal strain, meaning what is the current utilization grade of the geogrids? Are they close to rupture, or is everything still intact? So there was also some action plan behind this. So in case if thresholds would have been exceeded, then additional supporting actions would have been to be taken. And what I like about this example, this is a typical setup, how it looks like in most of our monitoring projects when we use distributed fiber optic sensing. So very often fiber optic sensing is not the only technologies being used, but it complements the traditional technologies. Like in this case, we do have here total station measurements, classic total station measurements to points on the surface of the structure. So with this, we do know about absolute displacements, we see rigid body motions, we see possible tilting or settlement of the whole structure. But what we don't see, we don't have any idea about the internal strain distribution. And this is where distributed fiber optic measurements comes into place. So here, we are going to take a look at one-dimensional longitudinal strain. So strain basically being a length change divided by base length. So here we're interested in how does the strain looks like in longitudinal direction. What we can see that the complete measurement is possible with just one single instrument at one single measurement location. We have here a measurement loop, overall about 2 kilometers in length. The instrument is located in one central measurement container, and from that, there's a fiber going to the first cross section, going into the dam, out of the dam, up one level, into the dam, out of the dam, up one level, in and out, and so forth at the first cross section, at the second cross section, the third, and the fourth one. And here, the monitoring system had two purposes. So first of all, to determine the strain evolution during the construction. As you can imagine, you start constructing from the bottom, and as you start filling up more and more material on the top, you will see an increase of strain at the lower levels. But also, that system was meant to be there for the long term. So basically for the time until the full disposal site is being filled up, in order to see if there may be some problematic situations occurring during the operation of the disposal site. So let us take a look now at both situations. So first at the construction time, and then at the long-term strain development. So what we can see here is the strain development during the construction phase. We are going to take a zoom look into one of the cross sections. Actually, we are looking inside of the earth structure, an area which is typically not accessible with classical geodetic measurements. And what we can see, as expected, we can see an increase during the construction as more and more material is being piled up on top of that level. However, even after construction stopped, we can still see some creeping behavior, which slowly stabilizes. So here we are at strain rates of about 1% or a little bit more, which is still perfectly fine for the sensors, but also fine for the geogrids as well. So this was the construction phase. I want to give you some pictures how the structure looks like. So here we can still see right after construction finished without any vegetation. This is then 2016. We can see already grass coming up again. However, the landfill just started. And about 3 years later, from the same spot, you can see that the disposal site is almost full. You can see here that just a massive amount of volume, which is coming from the 3 construction sites. When we're going to take a look now at the long-term strain evolution, we do see, again, the starting phase. We can see everything is stabilizing, and suddenly we do see a jump in the data series. So between these two measurement epochs, suddenly there was a massive increase of strain. And here the question was that what happened at this specific point in time. And actually nothing was wrong with the structure itself. There were some modifications being made. When we're going to take a closer look, we can see here a curved section of the structure with a rather narrow curve, which works only for, let's say, regular sized trucks, but not for the big dumpers. In order to be able to cross or to pass by here with heavier trucks, it was a need to actually fill up this area as well, what you can see on the right-hand side. So we can see here the situation before and then the situation afterwards. So here there's much more space now for making the turn, which enables now heavier machinery to get around the corner as well. So we do see the impact of this modification of the structure. Everything is still fine, so no problem for the geogrids, but still we can detect those changes. So everything worked fine during the construction phase, small strain development after construction, then that one jump due to the modification, and everything was okay. And actually now the whole landslide is, the whole area is filled up, and now the reinforced earth structure cannot topple over anymore anyhow, since now the disposal site is more or less being closed because it became full. So this was one example where we can already see that technology works for several years. We can detect changes. However, in that application, the main focus was just measurements along the fiber axis. So here the main result was longitudinal length changes. But let us take us a look now at a different application. So next, what I would like to show you some applications in tunneling. Regarding tunneling, here we have done a lot of work within the last 10 years. So actually we have equipped outer linings with fiber optic sensings. We have equipped inner linings with fiber optic sensing. We have equipped tunnel lining segments with fiber optic sensing cables. And we have also retrofitted existing tunnels by placing fiber optic sensing cables on the already existing surface of the tunnel. So we have installed in several railway tunnels, being the Colm tunnel, the Semmering-based tunnel, the tunnel chain granite style at the Zentrum am Berg. We have equipped existing highway tunnels like the Blabuch tunnel and Tauern tunnel, and also a newly constructed tunnel on the highway S7. And we are also here involved in a sewage tunnel project. But what's the benefit of having distributed fiber optic sensing in tunneling? I want to show you this by giving two examples, one coming from conventional tunneling and the other one from tunneling with tunnel boring machines. Let us first take a look at conventional tunneling. Typical situation that you can see here, classical monitoring, tunnel excavation and displacement measurements with total stations. When we talk about conventional tunneling, what you can already see on this picture as well is that the whole cross section is never cut out at once. So you usually have at least 2 or 3 steps. So first, the top heading is cut. Then this is temporarily supported with steel girders, anchors and shotcrete. And after a few days, the bench and invert are being constructed. So you have the top heading advancing, and then with a delay of several days, you have the bench and invert. This, or the behavior of the lining, has to be monitored because deformations are basically allowed, but they have to stabilize after several days, or at least within the first 4 weeks. So monitoring is an essential part of the progress. Because of the monitoring results, you choose then how you continue construction. So you decide about the excavation round length, you decide how much support you need, how many girders, how many anchors, and also the thickness of the shotcrete layer. So monitoring has a direct impact on the construction sequence, on the construction speed, and on the material that is being needed. So monitoring is a must, and conventionally, this is done with classical total station measurements. So you can see here a situation with several cross sections with bireflex targets. All of these flashing points actually targets arranged in cross sections. So usually you have about 5 to 7 points along the cross section. However, what you can already see at this picture is you don't get a complete picture. So first of all, we only get a few measurement points at one cross section. You can also see the bench and invert cannot be monitored. And as measurements are usually carried out only once per day and only close to the tunnel face, you don't really get a detailed information about the long-term behavior. And like usual, with a tripod, you're always in the way. So basically the measurement itself do interfere with the construction progress. And here the idea is to use distributed fiber optic on one hand for the construction, but also for the operation phase of the tunnel. So the idea is several cross sections are equipped with fiber optic sensing, and because of the long measurement length that is possible, the instrument itself can be even outside of the tunnel. So the measurement itself do not interfere with the construction or with the operation of the tunnel. Of course, you need some time for the installation, but the measurement itself doesn't have an impact on either construction nor on operation. So how does this work in practice? You can see here one of the installations done by my team. So we can see the reinforcement grid and the fibers being attached to the reinforcement grid. So basically they are placed there to have a defined location, but the final bonding is being made with the Shotcrete. You can already see here 2 different colors of the cable. So one is a tightly coupled cable, which is sensitive to strain and temperature. And for the temperature compensation, we have a temperature sensitive cable running in parallel. So we have both cables in parallel. And on the right hand side, you can already see the shotcreting process, which is a rather harsh process. What is important to note is sometimes there's a discussion, can dark fibers being used? So dark fibers are fibers which are within communication cables which are not being used. For distributed acoustic sensing, yes, this can be done. But when we talk about high accurate strain sensing, we do need a specific strain sensing cable. And let us take a look now at the difference. So a communication cable usually consists of a huge number of communication cables, so a huge number of single mode cables, but the main purpose of the communication cable is data communication. So therefore, the cable should not experience anything which is happening on the outside of the cable. So therefore, the fibers can move freely, to at least to a certain extent, can move freely within that cable. So they could be gel filled, or there could be some air gaps in between. So we don't have a tight connection from the outer surface of the cable to the fiber core. So this is on purpose because the signal itself should not be influenced by occasions which happen on the outside of the cable. When we talk about a sensing cable, here it's the exact opposite. So here, these are tightly coupled, meaning everything which happens on the outside of the cable should be transferred to the core of the fiber. And so therefore for exact strain sensing, there's a need for specific strain sensing cables. For distributed acoustic sensing, communication cables can be used. For temperature sensing, depending on the application, you either need specific cables or you can use communication cables. When we talk about installations in civil engineering, first of all, the fiber has to survive the installation. Otherwise, the whole progress is meaningless. And therefore, there are different options. Here, just a few examples how such cables can look like. You could have a tight buffer fiber, meaning this is the pure fiber, glass fiber itself, with a buffer around it, which just thickens the fiber up and makes it a little bit more robust. The next one would be a fiber metal tube. So the fiber, and then there's a metal tube where the fiber itself is either clamped or glued within that metal tube. Then we can have extra additional layers also with some structure which bonds better with the material, for instance concrete. And if there are really very harsh conditions, you can also have some additional steel armoring around it. Usually you order those fibers on the drum. So you order a cable with a length of several hundreds of meters or even kilometers, and then you just cut off the length that you need for the application, splice the connector to it, and you have a sensing cable customized for your application. And those types of fibers are robust enough to also survive something like this. As you can see here, this is conventional tunneling where the shotcrete is put with high pressure onto the reinforcement grid, and also this is possible with fiber optics. So here the fibers, we never had a situation that during this process the fiber broke. We can perform measurements with the instrument far away, but it has to be noted, as a result, we get information what happens at fiber meter 354. In order to know or to give an interpretable result, we have to know where this fiber meter is geographically. What we usually do is we use conventional total station techniques and measure reflectorless the position of the cable. By doing so, we can relate every single fiber meter to three-dimensional coordinates. So we know at every given point in time where this fiber is actually being laid. And if we know that, we can then make a relation between fiber meter and spatial location. And when we talk about now the tunnel progress, what we can see here now, on the right-hand side, you can see our cross-section. Here we're going to see the strain profile, and downward progress advances now into this direction. So what we can see, as the tunnel construction progresses, we can see shortening as expected. We have here shortening, so negative strain. As we continue construction, we have a further increase of or decrease of the strain. And here only the top heading is being cut out. At the later stage, we can also see that the bench of invert are being cut out, and we can also see now here that the whole ring is being closed, and we can see how the whole cross section shortens. So we can make a display in a spatial way, but we can also then select individual points and take a look at how this strain develops over time. So we can also take a look at classical time series. And this is what you can see here. On the left-hand side, we can see the strain at given times, shown here with different colors. So each color corresponds to a certain time instance. And when we take now certain locations, we can also take a look at the complete time series. So here we have continuous measurement during the first weeks. We can see when we're going to take a look at the crown point, how shortening looks like. It's starting to stabilize. But as soon as bench and invert are being cut out, we can see another acceleration, which also stabilizes. So stabilization as expected, then further acceleration when bench and invert are being cut out, and then another stabilization phase. We can also see as soon as bench and invert are being cut out, we can see here also suddenly positive strain at the shoulder, as this can also go into that direction now, but all of this stabilizes. The bench and invert stabilizes, and then as the next bench and invert is being cut up, we see another acceleration, which also stabilizes. So everything normal. And when we're going to take a look at the long term, so here we can see what's happening over more than a year, so about 1.5 years. We can also see, we still see some strain, but everything is still in the normal range. So this is now embedding in concrete. We are still looking at strain in longitudinal direction. However, now we already have a curved element. When we talk about bridges, or when we talk about tunneling with tunnel boring machines, we have solid concrete elements. So this is now one tunnel lining segment. So usually a tunnel boring machine places, depending on the tunnel, between 5 to 8 or 9 of these segments. And also here we can utilize fiber optic sensing. So the idea is we have here a segment which is about 6 meters long, and we place a sensing cable into that segment. So we can route it on top and at the bottom, and not just only once, we can do it several times. So one layout could look like this. So we go here on the top, go down to the bottom, and now we can realize thousands of measurement points. So the conventional way would be, like you can see here, 2 vibrating wire sensors. So a huge element may only get information at 2 individual points. However, with the fiber optics, let's say if you would put 70 meters into that segment and measure with a spatial resolution of 1 centimeter, we would get 7,000 measurement points just within that one measurement, one lining segment. Here, the advantage is all of this can be equipped, let's say, under factory conditions. So when we're going to take a look at the tunnel lining segment factory, we can see here all the different reinforcement cages. We can attach the fiber temporarily with cable ties, but as I said, the final bond is made between the concrete and the structure of the cable. Then we have here a little box where additional cable length is being piled up, and also the connector is being placed, and the further production is just in a regular way. So you can see here how the reinforcement cage is placed into the formwork and the final segment after it is being cast. So does this work? We can do that in a complete tunnel, but we can also make a loading test. And in Austria, we do have the opportunity that we have here loading test facilities for tunnel lining segments. And this is what you can see here. So in this facility, we can either apply vertical load and or horizontal load. But what I want to show you today is an example where vertical load is applied to this tunnel lining segment. What we're going to see now, we make vertical load, and we have here the load regime. So we increase the load, decrease the load, increase the load, and we have here 3 different areas. So basically we have here one fiber top bottom, another top bottom, another section at the top of the bottom. So all of this is just one single cable, but 3 times running at the top and 3 times running at the bottom. So let us now take a look what's actually happening when we start applying the load. We apply the load, and of course what's happening at the top side where you apply the load, you will see shortening, and in the bottom side you will see positive strain. So you will see on one side shortening, and the other side elongation. Please note that in this case the force itself is not within the fiber axis, it's actually orthogonal to it. So we can also depict deformations which are orthogonal to our main sensitive axis. And this is something that we can also utilize when we talk about anchors or soil nails. So this is one example of a highway construction site where temporarily that slope was stabilized with soil nails. And here the idea was to also get information about how those soil nails, which are also sometimes called grouted anchors, behave during the construction. So what we can do, we can equip such a nail with fibers, and if we place a fiber at the top and at the bottom, meaning above and below the neutral axis, we can also depict curvature changes. So in this case, we do see when this beam starts to bend, we will see on the top side positive strain, and on the bottom side negative strain. And this can be used to calculate the curvature. So the difference between these 2 strain readings divided by the distance gives us the curvature. So this would be the case if the overall length, so meaning the length of the neutral axis, stays the same. If the length of the neutral axis changes, we can also take that into account, because the average of both readings gives us the longitudinal change, and from this we can also then calculate the curvature. Just one example how this can look like. We could have here our soil nail. We have a little groove where we have the fibers being placed, strain sensing fibers, but also one for temperature compensation. We run it at the top and at the bottom. So here just another example how this looks like. Of course, before we install it on site, we usually perform testing of the whole setup. And in this case, we can see here a section which is about 5 meters long, and we apply load. So we have here the fiber on the top, the fiber at the bottom, and in the central area, we apply some vertical load with a fixed bearing at the left side and the floating bearing on the other side. Of course, we want to know if our fiber optic readings are reliable. So therefore, we have some reference systems. So we measure here with digital image correlation the displacement, but also with total stations to prism targets. So how does the result look like? When we take a look at the strain, we see on the top elongation, at the bottom shortening. Then here, the point where we are connected, here we have then here the turning point. Here we come from negative strain to positive strain and the other way. So we see almost perfectly mirrored behavior. Since we know the distance between the two fibers, we can use this information to calculate curvature. So this is the curvature. It's curvature in one direction, curvature in the other direction. And as curvature is the second derivative of displacement, so when we know the boundary conditions, which we do in this case because we have a fixed bearing on one side, we can determine the displacement curve by double integration. So when we use now the curvature readings and perform double integration, we do get the displacement curve. And this can be compared to theoretical numerical models, what you can see already here, or we can also do a comparison with digital image correlation. So here we can also see a very good fit. So the dashed red line is image correlation, the purple line, the cyan line is the distributed fiber optic sensing. So also here we can see displacements of about 4 centimeters, and the remaining deviations are a few tenths of a millimeter. So this is in a lab condition. But does this also work on site? Let us take a look. Here we have the on-site installation. We've equipped 3 anchors with the distributed fiber optic sensing in one cross section. And what I would like to show is now the result of one of the nails. We can see strain top at the bottom. We can see similar behavior here, so positive strain here, meaning an overall length increase, but we can also see here different behavior on this in this area. And we use this and calculate now the curvature and double integrate. We can see then the bending shape. Like with borehole kilometers, we have to make some assumptions about the endpoints. In this case, we assume that the endpoint and end direction are being stable, and by doing so, we can see then that this anchor also has a displacement shape. So it's not just elongated, but as you can also imagine, when we have here this anchor and further material is being removed, that this anchor will also start to bend, and not just having longitudinal strain. So the main point here is if you make the right routing, you can also detect the formations orthogonal to the sensitive axis. So far, we have measurements made without any gaps, so no blind spots. And this is essentially important when you don't know where your problem will occur. So let us take a look back to the tunnel lining segment. So we said when we apply vertical force, we do see positive bending on one side and negative strain on the other side. So what happens when we even increase the load furthermore? What we do see now, we suddenly see spikes occurring. So we see certain location where we have a massive increase of strain. And this these spikes increase in height, and also their number does increase with further increase of load. And this is now really interesting, because actually what we can see here is the development of cracks. So we can now, because we have no blind spots, we can exactly tell when and where cracks occur. So how is that possible? We measure longitudinal strain. So strain is nothing else than the length change divided by the base length. In the initial situation, for instance, here with the concrete beam, we have a perfectly intact beam. So we have no strain, no force, nothing. When we start applying load to it and we suddenly have a crack, in theory, a crack means we have a certain crack width, delta L, divided by base length. But before, the length of the crack was 0 because there was no crack. And this would mean we would have a value, let's say 0.3 millimeters divided by 0. So a crack, in theory, does mean a strain increase up to infinity. Obviously, this does not occur because now, depending on the used cable and the used measurement principle, we will see a strain peak like this here. And how this peak looks like, so how wide it is and how steep it is, this depends obviously on the crack width. It depends on the spatial resolution of the instrument. It depends on the cable that is being used. And if you apply the fibers not inside of the concrete, but you mount it on the surface, it also depends on the adhesive that you use in order to connect your fiber to the surface of the beam. And by taking a look or counting those spikes, we can see how many cracks and where cracks do occur. Of course, we also verified this independently with surface-based measurement, in this case with a camera-based system. And we can see a nice fit of the internally measured cracks with the cracks on the surface. And this can be now used on how different lining segments to perform. Depending on the geological situation, there are different types of lining segments with different amount of reinforcement, maybe also different concrete. And for that specific tunnel site, you can see here type 2A and type 3, how they perform differently. So type 2A is the regular lining segment, which shows at higher loads significant cracking. The more robust lining segment of type 3, this shows no cracking up until the last loading step. So here now this technology can also be used for the verification of the performance of the lining segments during load tests. However, it's not just only possible to do it under lab conditions, but it's also possible to do it in real environment. So again, the same idea, we have one central measurement location, which can also be outside of the tunnel. And from this, several rings equipped with that fiber optic sensing cable can be measured. So you can see on the right-hand side how this specific tunnel looks like. We can see here the lining segments, and actually this picture was taken from the top of the tunnel boring machine. And as a typical result, we can see here the strain of a whole cross section. So we can see here 1, 2, 3, 4, 5, 6 lining segments. We have embedded that fibers in 2 layers. We have here at the bottom and the top. We can see, as expected, shortening. However, we can see here some areas where the embedding of the ring isn't perfect, but we can also see positive strain. But we can also see that this strain curves continues nicely. However, regarding fibrometers, this is a totally different fibrometer than this one, because the fiber is going forward, backward, forward, backward, forward, backward, and then coming to that location. So though these are spatially close to each other, in fibrometers, they are far apart from each other. Again, if you go back, all of this was measured in one measurement round. So the instrument itself is far away. We have here the routing, a connection to the next segment, routing, connection to the next segment. So all of this is the result of one single measurement. Okay, so these were some examples. Just note, we can measure longitudinal strain, we can measure strain orthogonal to the sensitive axis. We can also detect and localize cracks. But one thing which is important to note, please remember, when we go back to the initial start of this presentation, we measure with light. So we send light into a fiber and we measure what is coming back. Since we measure light, we can measure the reflected intensity, we can measure frequency or the inverse wavelength, and we can measure the phase. So these are our raw readings. Temperature, intensity, phase, frequency, or wavelength. But what we want to know is either strain rate when it's about acoustic sensing, or temperature. So we have to convert our raw measurement readings into our desired quantity. And here, very often, a lot of the accuracy is being lost. Because you could have a very accurate raw measurement, but if you convert it with a wrong conversion function to your derived quantity, you can easily have an error of 10 to 20%. So it's really important that you know the exact relation between your raw measurement and the derived quantity. And for this, we have developed several calibration facilities here at Graz University of Technology. A lot of them are in our measurement lab. So we have a measurement lab where we have a static strain calibration facility. We have temperature chambers for temperature calibration. We also have some test setups according to C-form for dynamic testing. And we also set up test facilities for the long term, where we pre-strain fibers to a certain extent and measure their behavior over years. Regarding acoustic sensing and the base noise of those sensors, we also utilize the sound studio at the university, where we have a zero noise environment and also no vibration. Just a typical result of one of those calibration runs. Here I want to show you strain calibration. So our facility looks like such. We have here a 28-meter long interferometric bench where we can stretch short sections of a cable, but we can also stretch 28 meters in one go. We apply controlled strain, so we elongate that cable with the translation stage. Our reference reading is a reference interferometer, and as if we are using very stiff cables, we could have potential tilting. We also have tilt meters here. We measure the force and so forth. Finally, what we do get is a relation between applied strain and the raw reading. So in this case, this is a high resolution strain measurement, which gives us as a raw reading frequency shifts. So we can see here how, in this case, the frequency shift decreases with applied strain. So everything looks nicely linear. What we always do is we make several runs. So we elongate, shorten, elongate, shorten, elongate, shorten. And with this specific cable, we do see that we have some run-in effects. So during the first stretching, we do have here significant deviations from the linear calibration curve. So here we have deviations up to 40 micrometers. But after that run, we still have some slightly high hysteresis effect. But generally, we're going forward and backward, and we have a noise in the range of a few micrometers. But it's really important without that calibration, and if you just use some standard factors, you could even have a slope value which is about 10 to 20% different. And this is something which has to be avoided. All right, so basically this brings me almost to the end of my presentation. What I wanted to show you today is that distributed fiber optic sensing can be used successfully in geotechnical applications. So we can determine longitudinal strain, we can determine curvature with the right routing, and if the boundary conditions are well known, you can also make double integration, cover up with displacements. As we don't have any gaps, we can localize effects. So it could be cracks when we talk about strain, it could also be leakages in pipelines when we talk about temperature. It's a well-proven technology. So what I wanted to show you, it's really robust enough for the installation. So even Shotcrete works fine. It's long-term usable. Here the advantage is that at the measurement location itself, you don't have any electronic, you don't have any mechanical moving parts. It's just a glass fiber. And I know from a personal experience, I've embedded fiber optic sensing cables in that bridge that you can see on that slide more than 20 years ago. So I know from a personal experience, it works at least for several decades. What I also wanted to show you today is that calibration is crucial for reliable results. So I just have shown one example here. And from our experiences, fiber optic sensing very often doesn't really replace conventional techniques, but it complements them. For instance, in tunneling, we still obviously need geodetic measurements, but we may not need them that often. So we can thin out the measurement interval of the total station measurements and have less disturbance of the construction process when we don't have to set up a total station that often and fill those gaps successfully with distributed fiber optic sensing. Yeah, so this is an overview of what I wanted to show you today. We have lots of literature for this, so we have done also lots of publications. Some of them are listed here. In case if you need more information and want to have more details, just contact me and send me an email. I want to say it was a pleasure for me to make this talk today. However, all those projects were not just made by myself. The key to success is to have a highly competent and highly motivated team, and I'm really proud to be having such a team. So my staff is really well proven, even if it's climbing, if it's underground, could be nice weather as well. And with this, I would like to finish my talk, and I want to thank you very much for your attention.